Welcome to breadboarding. In the previous video we laid out a breadboard adapter to allow a 132-pin 386 microprocessor to be installed onto a breadboard. During this video what we're going to be doing is soldering the pins into the green protoboard there, wiring it all up, and then looking at building and testing a reset and clock circuit, which we'll use in later videos to test the CPU with. This is video number 4 in the 386 breadboard PC project. And in this video, we're going to be finishing the 386 breadboard adapter and building the power supervisor, reset and system clock circuit. And we'll test this in preparation for testing the CPU in the next video. So here's the breadboard adapter just before I start soldering everything. So you can see this diagram here is a bit messy, but it's all color coded and it basically just shows where I've actually taken some of the spreadsheet definitions and I've made these labels. So this is for the underside, so we've got to be really careful when doing this. So we're looking at this from the top side, so things are reversed. So it can be a bit tricky thinking in reverse sometimes. So what we've got here is these are some power rails. So I've managed to actually squeeze in the extra power rails that I didn't fit down the outsides there. So that means that these power rails are fitting in one of these sort of breadboard power rails just underneath here. So this should mean that we get good power everywhere. And we've also got a little extra connector up the end here. So this has got the extra address lines. So address lines 24 to 30, which are not used by the PC, but I thought it might be quite useful to at least be able to pull those out. And obviously what we need to do now is to solder in all of these pins down here. These 19mm pins just use this sort of gauge in the end here to make these a little bit longer so they stick out, and I've got enough clearance to plug in DuPont connectors on the end there. What we're going to be doing also, these are some wiring combs that came from my Roadrunner wiring pen kit, but these will be useful. We'll put those on the underside of the board here and we'll put those along the sides here, and it just means that when we're routing the cables out to the various pins we can just sort of guide them a bit so that they don't all clump together. So I'm just going to now go off and solder all of this up, and then based on this wiring diagram and the spreadsheet that I showed in the previous video, this spreadsheet is what's being used to generate these labels. You can also see over here, this is where I've got the extra power rail, so I'll be putting in the pin IDs on here, and this is what I'm going to be using to tick everything off, so you can see that we've got the CPU N2, L1, K2. I'll be using that, and the diagram on the right hand side here, I'll be using that to try and wire this up, and then we'll also be using this for doing the testing. So I'm going to speed this up. It's going to be very fast. It's probably only going to take a couple of minutes to wire this up. It's probably about 3 or 4 hours if elapsed time. The big black thing on the right hand side there is the fume extractor, which I've got that cleans the fumes coming off the solder here. I'm just alternating where I'm actually doing the soldering so I don't melt the plastic in the breadboard there. Just doing the power connectors there. And in fact the wiring up took about 5 or 6 hours in fact. Okay, so all that's been soldered, so we'll see when we try and pull this out if it's been done properly. So what I'm going to do now is to unplug this, and then we're going to solder these leads in, and then once we solder the leads in we can just pull out these little connector bits that are holding the 132-pin PGA connector together. Okay, so we're just going to do, not going to do every single one of the socket pins here, just trying to do 3 or 4 of them for each of the rows of pins so they don't move around. And just do the address connectors there and take out the pin. Okay, so that's all the soldering done. I have just checked that the CPU will fit in there, hopefully. I don't want to shove it in at the moment because it's going to be difficult to get it out. So all that is all soldered now. So now what we need to do is to flip it over and put the various labels on that we had earlier. I'm going to stick those down here. Now I'm thinking of taking out the plastic strip there. I think it's not really needed for these things now they're located in here, so I'm going to carefully take the plastic strips out, and then we're going to start wiring up the wire wrap. And I probably will not record the wire wrapping because it's going to take quite a long time and I don't think it's going to be particularly interesting to watch. So when we come back, hopefully we'll have it all wire wrapped up and I've done some testing of it, and we should then start to be ready to plug this in and hook up a clock circuit to see if we can get any life out of the CPU. Now, in the previous video, I did show this wire wrap tool under the microscope, but I forgot to actually do the bits showing the end and how the actual tool works. So you may just be able to see there's a very thin slot down here, and there is a couple of holes in the end. And what we do with our bit of wire here is we need to be very careful to push the wire in, and there's a hole at the very top near the slot. And if we get it right, then you can see that the wire will actually go in through that hole and then go in down that slot. So what I'm just going to do is to show you what it looks like at the end of this tool, because if you've never seen one before, it's not immediately obvious how it actually works. Okay, so this is the end which is used to wire wrap, and you can just see there's a bit of blue light, small bit of blue light at the top there, and that's the hole that goes at the top of this going into that slot, and that's where we need to push the wire into. And the big circular hole in the middle, that's where the pin goes. So what we do is feed the wire in through that hole, try and push it in as far as it will go, and then put it over the pin through that hole and then rotate. And if you can see, there is a little bit of a raised sort of edge at the bottom of that, and that helps to actually wrap the wire. If you've never seen one of these things before, it's quite almost magical how it actually manages to wrap the wire on. And the key thing you really need to worry about is making sure the wire goes in the top hole there, not in the central hole. Now, if we have a look at the other end, this is the unwrapping tool. And the unwrapping tool is a bit simpler. It's just basically got the hole for the pin, and you'll see there's sort of a raised edge there, and that will basically get underneath the wire wrap. And if you rotate it the opposite way to what you used to wrap the original wire on, then it will start to undo it, and generally after a couple of turns it's loose enough then to be able to pull off. So that's the wire wrapping tool. So I've finished wiring up the board, and we've got the processor down here, and you can see this is the 132 pins that we're needing to plug this adapter. I have checked that this will actually fit, although I don't want to plug it in quite yet until we're sure that everything else is wired in, completed. Took a little bit longer than I anticipated. Probably takes about 2.5 minutes to do each wire, so that's a connection at each end, and so that means you can do about 8 pins in about 20 minutes. So in total it probably took the order of about 5 hours to actually wire all of this up. So if you just have a look on the underneath side of it, you can see now that the wiring mess that we've got on the diagram now here has now been reproduced over here. We've got the little channels here that I used from my wiring pen, so that helps to steer some of the cables. And I have gone over each of these connections, and with the microscope and actually checked that all of those are actually looking okay. And I've also tested every CPU pin to make sure it's attached to the appropriate pin. And you'll see on the front here then these are all of the pin layouts that I actually included on here. And we've also got the power here, so we've got 5 volts and ground, 5 volts and ground. Down here we only needed the 5 volts, we didn't need any ground. So to test this further, we're going to need to plug this into the breadboard, and I'll do that off camera because it will probably be quite fiddly to get the best part of about 120 pins all to fit into the sockets cleanly. Now we've wired everything up and the adapter is ready for testing, we also need to worry about how we can actually test the CPU. So this is the diagram from the internal design document for the COMPAQ DeskPro 386. We did cover this a number of videos ago, and there are a couple of sections we need to worry about for this. So down the bottom here we've got the 32 MHz oscillator with a couple of CMOS buffers that provide the voltage levels needed for the 386 chip, and this 32 MHz signal is then divided by 2 to provide clock 16, and the clock 16 is then also used to clock the reset signal coming in here to make sure that the reset line going into the CPU meets the timing requirements. Now we can't just plug the clock into the CPU here, there's quite a few other control lines that we need to set at the appropriate values. And what we're going to be doing here to test the CPU, it's something that we've done in some of the earlier series videos. So in the Breadboard PC version 1, there's a couple of videos here. So one where we're looking at the reset and power supervisor circuit, the system clock, which we don't need to cover in this one in that it's a bit different for the 386, but there's also the CPU no operation free run. And we're going to be making use of some of the things that we did in these two videos. So I include the links to these videos at the top of the screen where it actually makes sense. So if we look at the 386 datasheet, in this document we'll be going into this throughout the series, but the bit that we really need to look at for the moment is what are the extra control pins and things that we need to set up in order to get the CPU working. So around page 67 we've got this table here, and I'll actually got a copy of this in the slides, and I've annotated this so we can actually make a note of what we actually need to do. So this is the table, and initially we've got our clock 2. So in the original DeskPro this is a 32 megahertz clock, but we're just going to use half the clock speed. This means that the core CPU clock will be about 8 megahertz, and that was a frequency that we used in the Breadboard PC version 2. So I know that the components and things will work fairly happily over breadboards at a CPU frequency of 8 megahertz. Now we've got 32 data lines on 386, but in fact what we're going to be doing is making use of the bus size 16 signal down here. So if we tie this low, then in fact the processor will only use the bottom 16 bits of data lines, and I've got a test board here that I can plug into the lower 16 data lines here, and we're going to put in the no operation code. So no operation just gets the processor effectively to do nothing and go on to the next instruction, and the hexadecimal code for that is 90 hexadecimal. So what we would expect to happen, and this is covered in the video that I'll include the link up here where we've done testing previously using no operation code, what we'd expect is that the address lines will just cycle through the full address range. So we'll be able to use it to test that all the address lines are actually plugged into the right pins to see if it's actually counting properly. There's a couple other pins, so the next address request we'll disable by tying high. We've already said the bus size 16, we're going to set this low, so we only have to worry about setting the bottom 16 data bus lines to be the no operation code. We're going to wire the ready signal, which is active low, to be low, so that means we don't have any wait states. We're going to tie the bus hold request to be low as well, so that the CPU controls everything. There's a couple of signals here to do with the maths coprocessor, so we'll set those so that they don't take part in anything. One thing to note is that during reset, if we set the busy signal to be low, then in fact the processor will go into a self-test. So we might do that if we have any problems, and certainly perhaps in the next video we might try and see what happens when we use the processor built-in self-test. Then we've got the main maskable interrupt request, which we need to tie this low to disable it, and similarly the non-maskable interrupt will set that low to disable it. And then we also need to make sure that we sort out a clean reset signal. So the 386 processor uses an active high reset signal, which is a little unusual. A lot of the earlier microprocessors, certainly the Motorola ones, tended to use an active low reset signal. And what we need to do for this really is to make sure that we've got clean power before we actually bring the processor out of reset. And also we might want to debounce a reset button so that we don't end up getting noisy reset signals. Now in the previous series what I've done is used a power supervisor chip. Again, there will be a link to the video where I covered this. This went through the datasheet and explained exactly how it works. But basically what we've got here is an input from a reset button. We've got a couple of signals to determine what tolerance we want for the power supply, and also the timeout for the watchdog timer. And coming out of this, we actually have an active high reset and we have an active low reset. Now the key thing we need to be aware of is the active low reset is an open drain, open collector. So unless we put a pull-up resistor on here to 5 volts, we won't actually see anything coming out of here. So that caught me out a little bit when I was first doing this. And I've also, in the previous projects, wired up a green LED and a red LED. So the green LED means that the processor should be running. The red LED means that it's in reset. Now, there's one other signal we need to worry about here. The watchdog strobe here, if we don't have a signal on here every 600 milliseconds, then in fact the watchdog here will decide that the processor must have stalled or hung, and so it'll actually reset it. So if this was in a microcontroller or an embedded project, then we might want it to automatically restart should it actually stop responding for a while. But in our particular case, we're just going to plug the strobe into one of the other clock signals, so at least that it gets the appropriate activity and doesn't actually push the processor into reset. Now the KiCad diagram we've been working on, I've almost finished it. There's just a couple more of the 32-bit memory module I need to do at the top here, but the vast majority of the rest of it is actually all done. It needs to be checked and run the integrity rules over it, because there's probably going to be quite a few mistakes and things. But for the CPU board, you can see here that this is the oscillator, we've got the buffers, we've got the one flip-flop that divides the input clock to give us our clock 16, and also then actually drives this flip-flop here to clean up the reset signal so it matches the 386 reset requirements. So I'll go off and wire that up. Okay, so I've wired up the test circuit. So this is the reset button, and when the green LED is on, then it means that the CPU should be running. When it's in reset, then the red LED should be on. This is our 16 MHz crystal oscillator. This is our CMOS buffer, which actually provides the correct voltage levels to feed off to the CPU. At the moment, I've just got an oscilloscope probe on the output here, which is through a 22 ohm resistor, which is what the COMPAQ DeskPro had. Just make sure this is on the oscillator output, this other probe. Then the output of the oscillator goes off to this flip-flop over here. So this is a 74F74 flip-flop. So this is a very fast flip-flop. So it's going to be capable of going at least 32 megahertz or more, and potentially could even run at 66 megahertz. Then the output from this is our half-speed clock, which is used for a lot of the other bus timing. So it's known as clock 16 on the original DeskPro because we were using a 32 megahertz crystal. But in this case, our output here is going to be 8 megahertz. And then the output of the reset from our power supervisor is actually going into the other side of this flip-flop. This is to make sure that reset changes state actually on the rising edge of the clock 16 output here, and that's the requirement from a CPU point of view. So I'm just going to turn it on. I've got a logic analyzer set up on it and also the oscilloscope. So if we just show the oscilloscope first of all when we power it on, you can see it in the top right hand side there. Okay, so you can see that we've got some frequency signals there. If I press the reset button, we should see the red light go on. Yep. And I'll release it, and then after a short delay, then the green light will go on. So we've got our frequency signals. If we just go to the full screen here, so you can see that the blue one is actually the output of the crystal, and it's about 16 megahertz down here. And the one above it is the output going through the buffer and through the resistor going to the CPU. So you can see that there is a little bit of bounce around here, but it's within the acceptable ranges for the moment. And if we now just turn it off again and go to the logic analyzer, so the logic analyzer shows the 5 volt power supply, so this will start recording when the 5 volt is switched on. We've got the output from the power supervisor reset, the input for the reset button. We've got our main oscillator output, so this is the crystal oscillator output. We've got the clock input into the CPU. We've got our divided by 2, so it's known as clock 16 on the DeskPro, but it's actually 8 megahertz here. We'd expect to see the CPU reset slightly delayed from the other power supervisor reset signal there. So I'm just going to set this running. I need to set it quite fast, so 200 megahertz to be able to get the frequencies here accurate, but it's too fast really to be able to look at the push button, so we'll do that in a few minutes. So just turn the power on. Okay, so what we can see here, we've got a period of time, probably about half a second here. We can see that once the 5 volt supply has stabilized, then in fact the reset goes active. See, the reset button is just, nothing's happened to it, it's just waiting for the power to come up. Now, if we actually go a little bit along here, you can see that the Power Supervisor chip takes the CPU out of reset after about 200 to 250 milliseconds. So basically it keeps the CPU in reset whilst everything's stabilizing. And if we have a look then around this sort of time, we can see the oscillator signal. So this is the crystal oscillator. So if we have a look at the top right hand side there, it won't always exactly fit 16 megahertz because we've got a bit of an odd frequency here. Because we're sampling this 200 million times a second, it's never going to quite be exactly 16 megahertz, but it alternates either side of 16 megahertz. So that is the output from the oscillator. Then this is the buffered output that goes to the CPU. Again, it is a similar frequency. It's just the duty cycle here will be slightly different due to the way how the voltages are being recorded by the logic analyzer. These are recording at TTL values rather than CMOS values. And then we've got our clock 16, which is the main clock divided by 2. And this is the one that a lot of the bus signals will be based on and clocked on. You can see here this is actually at 8 megahertz. Now, if we have a look at the CPU reset here, if we just zoom in a little bit, so if we put a marker of when our supervisor ends the reset and when reset actually ends for the CPU, you can see that in fact what's happened here is that the reset output here is weighted until the rising edge of this clock 16. And if we just put another, you can actually see the gap there, that's about 5 nanoseconds. So the F-series chip is about 2 to 4 nanoseconds. It's about as fast as this logic analyzer can detect. So what this shows is our reset signal will change on the rising edge of the clock 16, which is what we'd expect it to do. So now if I run this, and what I'm going to do now is to change the triggering to be on the reset button going high. So changing from low to high. So that means if I push it down and we start this running, and then when I release it, we should then see some sort of trace. So I'm just going to press the reset button down, collect. I pressed it a couple of times. We might just get more than one press there. You can see that in fact there's a bit of bounce there, and what the power supervisor do will prevent that from actually causing multiple resets. You can see this is when I released the reset button the first time, and basically about 225 milliseconds afterwards then the CPU came out of reset, normal running. Then I pressed the button again, and you'll see then that there is a short delay from when you press the button. That's the bounce on the button. You can see it's about 3 or 4 milliseconds from when you press the button for it determine that we finished any bouncing, and then it puts the processor into reset state, and you can then see that the reset button again has some bounce there. And the advantage of using this power supervisor circuit is that the reset button bouncing can cause problems, certainly when you're trying to record logic analyzer signals after a reset on booting up. Having these sort of spikes around can make things a bit more difficult to get clean analyzer signals. So it looks like the power supervisor circuit and the reset button is all working correctly. Now the other bit of the board over here, this is I've got this sort of board with some dip switches, and these two dip switches are actually set to provide 90 hexadecimal, which is the no operation code. So the purple end is the least significant bit and the black end is the most significant bit. So both of these basically have pull-up resistors to 5 volts, and when the switch is in fact turned on, it actually grounds that to 0 volts. So these two outputs will now be used to go into the data lines for the D0 to D15 on the CPU. And that will mean that every time the processor looks for an instruction, it will see that it's actually the no operation code. And what that should do is result in the address lines just cycling around through the entire address range. So now we know that this board's working, I'm just going to switch back and have a look at the CPU breadboard adapter. So this is a photo of the breadboard side of things, and I've already put in all of the power wires here. So because I left some gaps in the pins going along here, there should be sufficient space for these wires to connect to the power rails along here. There's one or two places where there weren't sufficient gaps, and so I've had to connect the pin through to the bus rail on the other side. But what this means is that all of the power pins should all be wired up. And then if we have a look at the assembled breadboard adapter, so this is with the labels are now all being glued on. So we have the A1 pin in the top right hand corner here. So we need to be careful when we put the CPU in, because the Intel i386 will actually be upside down when the corner bar for pin 1 is actually up the top right hand side here. So all of these things have been pushed in. It is possible to pull this out of the breadboard. It's just it's a bit fiddly because there's so many pins here plugged in. It takes quite a bit of effort to actually pull it out. But I have done lots and lots of testing on this. So going through this diagram, so this is the top-down view. So we have to make sure we get the top-down and bottom views sorted. So what I've done is gone through with the meter and done continuity tests between all of the various pins and all of the pins down the side here. I've also plugged it into the power to make sure that the power doesn't short out, and make sure that we've got 5 volts where we've got all the red dots, and also that we've got 0 volts on all of the green dots. So I've done everything I can do to ensure that hopefully we're not going to damage the chip when I plug this in. One other thing I have done is set my bench power supply unit. I've limited it to only 300 milliamps at 5 volts. And if we have a look at the data sheet, I'll show you why. So this is the 386 data sheet, and we can see down here the supply current, the maximum should be about 390 milliamps, typically 300. And because we're running this at about 16 megahertz, so we'd expect this to be quite a bit lower. So I've set it at about 300 milliamps, just so that if there's any problem, then at least it shouldn't cause any significant damage to the CPU. So I've done all the testing I think I can do. So now the time's come to plug in the Intel 386 processor. It needs to go in this way around, so you see this is where the corner is. So this is where pin 1 is, and there's a little dot there as well. So this is going to need to plug in there. I'm going to do this off camera just because it's quite awkward to film this as well as actually checking that all the pins are going in correctly. So I'll do that in a minute. And then we're going to add this other board here to the left hand side. So this has got our clock, so just need to wire in the clock, wire in these signals over to the data bus. So we've got the data bus signals down here and here. They're going to have these signals. And we've also got all of those other things we need to wire up. So I've also got to make sure that all these things are wired up. So once this is all wired up and the processor is plugged in, we'll then be ready to plug in the logic analyzer. And what I'm going to do with that is I'm going to put the 32 channel logic analyzer on all the address lines, and we'll see whether or not we can see the address lines going up in sequence. So I've now wired everything up. So we've got some resistors and things around for all those lines that I was showing that we needed to tie to 5 volts or to ground. I've wired in the 16 megahertz clock into the processor. The processor's now installed. I haven't pushed it completely all the way down. It seems to be firm enough. I didn't really want to force any of the pins. And you can see over here I've actually upgraded the data bus input here. So previously I just had 2 lots of 8-way dip switches, and now I've upgraded that to 4 lots of 8. So I've got the ability to set all 32 data lines to be whatever I want over here. At the moment, these are all set to 90909090, and I've also changed the BS16. So this is the bus size 16. I've now set that to 5 volts so that it uses all 32 data bits. I've also got my 32 channel logic analyzer over here. So this is an LA5032. So this is actually hooked up to the main address lines, and there's also a few control signals and things there. We're almost up to 30 minutes. I'm going to break the video there, and in the next video we'll be looking at actually testing the CPU with the logic analyzer and this circuit that we developed during this video. And if you don't want to miss out on future videos, then please hit subscribe, and if you check the bell icon with all, then you'll get notifications when new videos are published. If you found the content interesting and useful, please hit like. It just helps to make the videos available to more people. And if you like to leave comments below, then I do try and respond to most comments within 24 hours where I'm able to. Thanks for watching.